All right, shortest path algorithm. Here we go. Shortest path. The shortest path algorithm they present is Dijkstra shortest path, which again Google Maps is based off of Dijkstra. So it's a very modified version of it, heavily modified. All right, so the weighted edge is a non-negative number, aka how many minutes or miles, depending on which one you're maximizing or minimizing, I should say. The weighted graph, every edge has a non-negative value. The weighted p. All right, this is what we've been doing the whole time. So the shortest path is the path with the smallest weight. Shortest path algorithm, it's called a greedy algorithm developed by Dijkstra. Greedy means it starts somewhere and it always chooses the most immediate best value. It's greedy. That's what it means. There are other algorithms that instead of choosing the best value, it actually evaluates the entire system to figure out what's the best value to choose to be set up for the best position in the future. That's not this one. Those algorithms, they sound very daunting, but they usually have a cool trick to them. This isn't algorithms, so we're not going to talk about those. But I did want to mention this is greedy because it's a good idea to start thinking about different types of algorithms because you'll be taking algorithms, well, not soon, but eventually. Unless you're in the BA. Yep, that's spelled Dijkstra. Don't ask me why there's a J. Let's see. You got, all right, the weight. Okay, that's great. All right, this is how the algorithm works. Everyone got that? Good, let's do an example. So here's the graph. And we want to know what's the shortest path from 0 to some other value. The interesting thing about Dijkstra's algorithm is it gives you the shortest path from one node to every other node. So it's one to many. So how does this work? Well, you have your graph up here with the weights. You initialize at 0. You start at 0, and we're just for sake of argument, and then you fill in what weights there are to other nodes. So 0 can go to 1 with weight 16. 0 can go to 3 with weight 2, and 0 can go to 4 with weight 3. It can't go to 2, so we label that as infinite. The other structure you keep track of is weight found, aka have you found the weight or have you actually visited this node? It's what I prefer to call it. They like to have an array for it, so you can do that if you want to. It's probably faster than using a set, but have you actually visited this node or found the weight? Initially, it's true for 0 because that's where you are, and false for everywhere else. All right. Everyone good so far? Notice in graph algorithms, you're using a lot of other data structures. That's not going away anytime soon. This is actually the simplest one, because usually you use a bunch of them, but this one, there's only 2, and they're arrays, which is great. But it gets way more complicated from there on out. All right, this is what you do. You're at 0. First, you search the 2 arrays, you find the next element with the smallest weight that you have not visited. Which one is that? 3. You can't say 0 because you already visited. Haha, that's where we started. But the next one is 3 with a weight of 2, and you haven't visited, so we're going to go there. And what do? Well, we go to 3, and then we update these values in these arrays, in this array, sorry, with the new weight to get there. Well, it took 0 to 3, it took 2, but from 3 to 1 takes 12. So 2 plus 12 is 14, which is less than 16 that was there. So we update 1 from 16 to 14. We can't get to 2. We evaluate 4. We can go from 3 to 4 is weight 7, which would actually be 2 plus 7 is 9. But 3 is already there, so we don't update it. We leave it at 3. All right? Cool. Now we repeat. What is the smallest weight that we have not visited yet? 4. That we have not visited yet. Yeah. So it's 4 with weight 3. Okay, yeah, that's. So it takes 3 units to get to 4. So we're going to now evaluate 4. Notice that the 4 went to true. Now that we're at 4 and we knew it took 3 to get there, we use the number here, not the part in the graph. We use the number in the array. Very important. Use what's in the array. So it takes 3 here. Well, it takes 3 plus 13 10 to get to 1, so that's 13, which was less than 14, so we updated 1 to 13. But it takes 3 plus 4 is 7. Well, to get to 2, we've already, so, and that's less than infinite, so we go ahead and we update this value to 7, because that's less than infinite. Now that we've gone through this array, we repeat the process. What's the next node we visit? Yep, the 2. So set the true. In order to get to 2, it's weight 7. Notice that it recorded the weight. It didn't record that it's 3 plus 4 or 7. It just recorded that it's 7. Very important to always use the value in the array. So here it is 7. And we go through the array. Well, obviously 7 to get to 0, not happening. 2 to 10, or I'm sorry, 2 to 1 has weight 3. It took 7 to get there. 3 plus 7 is 10, which is less than 13, so we update that to 10. 2 to, let's see, we don't have any other edges, so we're done checking the rest of that. There's only one left, so that's 10, and then this is your answer. This is the shortest weight in this case to get from 0 to any other one. I say this in modified, some tricks that Google does. One, they don't record the weight, they record what your path was so far, so each of this smallest weight also has a linked list or some data structure attached to it that records the path that you've taken, obviously. The other thing that they do, and let's see if you can catch this one. This one might be a little difficult. Notice that every time in this array, or every iteration, you search the entire array trying to find the next lowest value that you have not already found. So they search an array. What would be a faster algorithm or data structure that you could still use an array for, and you just need to find the next smallest? I couldn't hear you.
You use a heap with the smallest on top?
Yeah, so they also use a heap when they search for the next one, and when you update the value, you just either sift up or sift down, because you always know what your parent and children are in a heap. Therefore, you're searching the next is now log of n as opposed to O of n in order to search it. You don't need to use a heap for your data structure. I'm just alerting you of what is actually way more efficient in Dijkstra's algorithm and what is used. Also pointing out that, hey, look, the heap helps again, seemingly out of nowhere. Bet you didn't expect to see the heap, right? All right. Any questions about Dijkstra's shortest path algorithm?
Yeah, how does Google Maps do a thing if it would have to search the entire graph, which is really big?
Okay, so, right. I told you a couple optimizations, the heap and the other modifications that keep track of the path. They do. So I have not looked at, when I worked at Google, they did not show me their algorithm, so I'm not breaking in an NDA here. I do know from reading that they make like hubs. So within your area, they get like the shortest path, they make that like a hub to connect to others. It's a heuristic. It's not necessarily the best. That's why sometimes it's not actually, Google doesn't actually give you the fastest, but they give you something close. Because yeah, if they had to do all the different points for every single possible turn and intersection in the US, yeah, that'd be ridiculous. But I mean, obviously they only need to zero in a certain area, hopefully, as well. So yeah, there's a lot of tricks they're doing. But when it comes down to it, once they have all their nodes and they've generated what they're going to evaluate, it's Dijkstra's. Cool. Any other questions? All right.